I'm Yougeng Lu. I'm now a fourth-year PhD student at USC, and my presentation topic is estimating hourly PM2.5 concentration at the neighborhood scale using a low-cost air sensor network, a Los Angeles case study. This is actually a part of my dissertation, and it's advised by Professor Jan Giuliano and Professor Rima Haber from Keck School of Medicine at USC. They are also the co-author of this paper, and this work has been published in the journal Environmental Research. So, as we all know, air pollution is a major public concern. It has adverse effect on human health, and it can cause various diseases in both short-term and long-term, such as stroke, asthma, and lung cancer. There are many factors can contribute to air pollution, like traffic emissions, natural emissions, and industrial emissions. These are three major sources of air pollution. Besides, other factors like meteorology and topography can also affect the distribution of air pollution. So for planners and policymakers, what can they do to mitigate or reduce air pollution? For me, I think planners can help at least from two perspectives. One is to improve the air quality monitoring, and then second is to develop some target policy and plannings to protect public health. So air quality monitoring is very important because it provides direct indicators that reflect the air quality conditions. So accurate air quality monitoring can help planners understand air pollution distributions and also develop more targeted policy and regulations that protect public health. Besides, we also like air quality monitoring to be at real time and at neighborhood levels. The real-time air pollution monitoring at neighborhood level is beneficial to provide guidance on short-term outdoor physical activities for local residents. So in this study, we focus on the 5 particulate matter, also known as PM2.5. And our major research object is to estimate PM2.5 distribution pattern at the neighborhood and hourly level, especially at unmonitored areas. So why do we care so much about the PM2.5 prediction at a high spatial temporal resolution level? Because we think we want to study the association between exposure PM2.5 and acute health effects. And we also think this high spatial temporal resolution PM2.5 prediction can help planners at neighborhood environmental plannings and designs. And also it can provide local residents guidance on short-term outdoor physical activities. So in this study, we choose Los Angeles County as our case study. Los Angeles County is one of the most polluted areas in the US, and also the LA metropolitan area is the second large metropolitan areas in the US. So different from the previous research on predicting air pollution, we are using the PM2.5 data from a low-cost air sensor network called Purple Air instead of using EPA monitors in this study. Both EPA monitors and Purple Air sensors collect PM2.5 data. And compared to EPA monitors, Purple Air sensors is much cheaper and require little training to operate it. So most people can afford to purchase Purple Air sensors and install them easily in their backyard to monitor air quality in their neighborhood in real time. So the low cost of this air purple air sensors make it possible to measure air quality in more locations. There are 361 purple air sensors in Los Angeles counties, while only 12 EPA motors at the same areas. So all of these advantages make purple air sensor a better choice if we want to predict PM 2.5 at the neighborhood level. However, since the purple air sensors are not designed for regulating purpose, their data quality is not as reliable as EPA motors and may be easily affected by different weather conditions. But recent evidence have shown their performance is keeping improving in the last few years. So in this study, we convert the PM 2.5 data to hourly levels and collect the data from purple air sensors from January 1st, 2018 to December 31st, 2019, totally 2 years. And as I mentioned before, because the PM 2.5 data from the purple air sensor is not that reliable, so we make some quality control process to clean the data before we do the prediction models. So we only keep the sensors with more than 75% data available, and we delete some extreme readings. And for each purple air sensor, there are 2 channels collecting the PM 2.5 at the same time. So we compare 2 channels readings and delete the channel, the sensors with mismatch. So we also divide our study areas to 500 meters multiply 500 meters hexagon grid. And in the final, we have get a little more than 2.5 million valid hourly PM 2.5 readings from purple air sensor. So as I mentioned before, many factors can contribute to PM 2.5 concentration and distributions. So we control as many variables that is informative to impact PM 2.5 concentrations as possible, both spatial and temporal varying variables. So we collect we control for the spatial temporal autocorrelations, the background PM 2.5, which is from the EPA monitors, and then the weather conditions, land use variables, traffic variables, and we also control the temporal dummy variables to control for the monthly, hourly, and also the seasonally variations in PM 2.5 concentrations. And in the final, we have 101 predictor variables in our prediction models. So in this study, we use a machine learning-based algorithm called random forest method to develop the PM 2.5 prediction model. So the right graph just shows the structure of a random forest method. So you can see for the random forest, we first divide our samples to several sample subsets, and each one called decision trees. So we have multiple decision trees in a random forest. And for each decision trees, it will develop its unique prediction models. And our final prediction is the combination of all the prediction results from all decision trees. And finally, we can get our random forest prediction. The advantage to use the random forest method is when compared to the traditional linear regressions, it can control for the nonlinear relationship between dependent variables and independent variables. And also random forest is very effective and productive at dealing with the big data issues. So in this study, we set the number of decision trees to 200 and the candidate feature attribute number to 30. And to validate and test our prediction performance, we also apply a tenfold cross validations to test our performance. So the mechanism of the tenfold cross-validation is we divide our sample to 10 groups, and we use 9 groups to be our training group, and then the last one as our test group. So we can get the test results for our prediction performance. So in this study, we run the overall cross-validation and also the spatial cross-validation, which we divide our training and testing group based on the spatial clusters, and also the temporal cross-validation, which based on the hour. So this slide shows the results of our prediction models. So you can see the y-axis is the predicted PM2.5 from our models, and the x-axis is the measured PM2.5, which is the real PM2.5 readings from the purple X sensors. And the color bar shows the densities of our the point. So the blue lines here is the 45 degree lines, and then the red dashed line is the fitted line from our models. So the R square equal to 0.93, which is very high numbers, and the RMSE is 3.23, which is relatively low when compared to our PM2.5 concentration. So this result shows our prediction models has a high prediction accuracies. And we also found a high predictive abilities of our models in space and time. For the spatial cross-validation, R square is equal to 0.88. And for the temporal cross-validation, R square is equal to 0.90. Both are very high numbers. So we just want to show the visualization of our prediction performance. So first we select one weekdays and one weekend days. For the weekdays, we choose Wednesday, September 18th in 2019. And for the weekend day, we choose this, the Sunday on September 22nd in 2019. And we shows the PM2.5 distributions for 2 different hours, at the morning peak hour at 9 a.m., midday at 2 p.m., and then the evening peak hour at 6 p.m. and the late night at 11 p.m. So we can see on the peak at the morning peak hour, we can see a totally different PM2.5 distribution on weekday and weekend. So for the Wednesday, we see a higher PM2.5 concentrations and a more dispersed PM2.5 distributions, especially along the highways. And at the Sunday, at the morning peak hour, we see a lower PM2.5 concentration and a more concentrated PM2.5 distribution at the urban areas. And then when we look at the late night, we can see on the weekend days, we see a higher PM2.5 concentration and a more dispersed patterns. And at the weekday late night, we see a lower PM2.5 concentration and more concentrated. So we assume that's because at the weekend night, late night, there are more traffic. And we also did the service prediction for wildfire days, which is happened on Sunday, November 11th in 2018. So it's during the Uzi fire, which happened near the border of Los Angeles counties. So marked in the black circles. So we can see from the color bars, for both 4 hours, we can see a very high PM2.5 concentrations across our study areas, especially at 9 a.m. So we assume the PM2.5 distribution is mainly affected by wind. So we can see the wind rose map here. The PM2.5 concentration is much higher when there's northeast wind and at the southwest region of our study areas. And then we also did a service prediction for a holiday on an independent day in 2019. And it's easy to find. We found a very high PM 2.5 concentration at late night at 11 p.m. We assume it's because the recreational fires and the firework at late night on the independent day, which caused a high PM 2.5 concentration at 11 p.m. So from our study, we think the low-cost sensors can supplement the conventional EPA monitor network to estimate more spatially and temporally resolved air pollution. And also, we think the predictive models can be used to capture some spatial and temporal patterns in PM 2.5 on less frequent and more extreme conditions like holidays and wildfire days. And also, these prediction models enable the highly resolved and improved exposure estimation in study of acute air pollution health effects and the study of environmental justice issues. And we believe this model can help planners and policymakers with neighborhood environmental plannings and designs. And also it can provide local residents guidance on short-term outdoor physical activities.